Hi, welcome to this episode of ProofPilot. We are here to talk about Sequence Lemma, but before that, I want you to hit the subscribe button. And if there's any question about the Sequence Lemma, I would gladly answer to them in the comment section. So we just talked about what a first countable space is in the previous video. An interesting property that first countable spaces have is that they are the type of spaces which sequences are sufficient to detect most topological properties. And to show why this claim is true, we just need the following definition. So we say a sequence of points in X are eventually in A if xi belongs to A for all of A's, but finitely many of them. So to give an intuition, what this means is, let's suppose that this is our space X and this is our subset A. This is what an eventually means, okay? This thing right here does not go out of A anymore from a point, okay? As you can see, this will be stuck in our set. So here is what the sequence lemma is. So suppose that X is a first countable space, okay? We will need this property in some of the parts of our lemma, and in some of them they are not necessary. For example, in the first part, it says that X belongs to A, to the closure of A, if and only if X is a limit of sequence of points in A, okay? This way of our assertion does not need the first countable space property, but this way it does. So I'm just going to prove this way. I think we have proved this way in the previous videos. So let's do the proof. I suggest that you just think about this, and the hint is you just need to write the definition of closure of A. Okay, it was the intersection all of B's, which B is a closed subset of our space and A is a subset of B. So I want to show that if X is in the closure of A, then there is a sequence which this sequence is the points in this sequence are in A, and the sequence eventually converges to X. To do this, we have to use this first countable property, and the way we use it is by the nested neighborhood basis. So we have to use this property, which we said will be useful in the future, and we can see why that was true. So let's just take a neighborhood of X, and this neighborhood will absolutely have an intersection with A, okay? And by the nested neighborhood basis, we know that there exists a sequence of open subsets and a member of this sequence will be contained in the neighborhood of X. And what we knew was that in nested neighborhood, we had this property that each of these members are the subset of the next member. So as you can see, if I take my sequence to be in these neighborhoods, it will suffices the limit definition, and this limit of sequence really exists in our set A. Now the second part of the lemma is really looks like the first one. Just again, this way of the assertion does not need the first countable, but this way it does. So we're going just to do this way. And again, we just need to write what an interior of A meant to us. it was the union of all b's, which b was a subset of A, and B's were an open subset of X. Okay. So if X belongs to this intersection, then again we can take a nested neighborhood, and we just take a neighborhood of X, and there exists a nested neighborhood because X is first countable. So there exists a UI which is a subset of our neighborhood, and X belongs to this UI. We just know that from the definition of nested neighborhood basis. Then, as you can see, it suffices the condition of eventually in A. So that's it. And the fun part of this lemma is that the third part and fourth part are deduced from the first one and the second one. So let's see what the third and fourth part are. A is closed in X if and only if A contains every limit of every convergent sequence of points in A. So as you can see, if A is closed, we knew that if A is closed, then A is equal to the closure of A. And we just had if X belongs to the closure of A, then X is a limit of a sequence of points. Okay, so such a sequence exists. And as you can see, our assertion says that A contains every limit of every convergent sequence of points in A. So if A is closed, A is equal to the closure of A, and X belongs to the closure of A, and so X belongs to the A itself, because A was equal to the closure of A. And for this way, it says that A contains every limit of every convergent sequence of points in A, and this again will be deduced from the first part. And the fourth part is really like the third one. I want you to think about this. It's the same procedure. It's not really difficult. Thank you for watching this. I hope you have enjoyed this video. Do not forget to hit the like button and subscribe to our channel.